Yes, last week we were discussing the main algorithm to draw Voronoi diagrams. It wasn't that complicated. Let's go through it once again, and then we will start discussing the details of it. So the input is already known. It's not that difficult. We have the set of points or sides, set of Voronoi sides, and the output will be simply the Voronoi diagram, but we will be representing it in terms of special data structure, which is called as doubly connected edge list. And we said that right now we are taking it as granted since we haven't discussed it in the beginning of this course. We will assume that in this data structure, there are some special, let's say, substructures where you can simply store edges, their relations with the vertices, and also we have some the reverse of these edges in the opposite directions. So what we are going to do in this simple algorithm, first of all, we need to do some initializations with the data structures. And the first one is about the event queue. Do you remember the type of events in Voronoi diagram implementation? Again, we were using a kind of a sweep plane algorithm. What are the type of events we have? You don't remember? Okay. I hope you have done the quiz properly. We have two different types of sites. The events, the first one is site events, and we can easily have them with the help of these inputs. These are all site events. And then secondly, we have circle events, and these are related with the position distribution of these sites on the plane. So initially, we are not aware of these circle events, but while we are moving downwards, we will see some of these and try to handle them later. So in the algorithm, what we do, we first initialize this event queue with all these site events, but the status data structure T is empty right now since we don't have the beach line. But once you have the beach line, then this structure will be filled with some, let's say, pointers or some information related with the arcs. And lastly, our last data structure is the output, the Voronoi diagram, and we are using an doubly connected edge list. So what we do in this algorithm, we check all these events. Until you are done with the events, you should do these operations. Remove the event actually which has the highest y coordinate, and then check if it's a site event, then handle site event. Call this function. If it's not a site event, then call handle circle event. So this is a very simple one, and the rest is some kind of, let's say, arrangements. And the seventh step, what we do, since we need to have a kind of a bounding box, and sometimes you will see that we have, at the end of this sweeping algorithm, we will have some actually arcs in the beach line. And these will be actually representing some half infinite edges. So depending on the size of your bounding box, you need to cut these edges and try to make them finite. And lastly, since we are using a doubly connected edge list, we need to traverse the half edges so that our data structure, this special data structure, is fully correct, and you can later output this data structure as a Voronoi diagram of your algorithm. So now let's focus on two sub-functions which are highly important. We have two events. The first one is site event, and the other one is circle event. Now this is the first one. How do we handle site events? So at the beginning of your implementation, you will have an empty status data structure since there is no beach line. So if T is empty, then what we do, we insert the PI, which is the first site event, into the beach line. so that our data structure, status data structure, will be consisting of just a single leaf, and that will be PI. And if it's not an empty one, then we'll continue with the other, let's say, steps in this function or procedure. So then what we do, we are searching. If you have another, let's say, site, assume that this time you have PJ, and you might have such a data structure for the status. It should be a balanced search tree. You may have such a kind of an, let's say, beach line status data structure. So then if you come up with another site event, then what do? You search for it, search for the arc actually alpha, which is above PI. Since if you remember the site events, let's say schematic, we have, assume that this is a kind of an site, this site here. Now I will draw in kind of a beach line. That is the beach line, okay? But if you come up with a new site, so this is our site event PJ. So what we were doing, if you remember, initially we will have a kind of a parabola having 0 width, and then as we go on, this parabola will get larger, and we will have 3 arcs. Yeah, that will be the new kind of beach line. So what we need to do in this second step, we will be searching this status or the beach line. We are looking at this beach line and trying to find the arc actually which is above PI, or in our example we have PJ, and the arc above PJ is this one. So this is the one actually we are looking. So I can say that this is arc alpha. If leaf representing alpha in our data structure, for instance, this might be alpha, and if it has a pointer to a circle event in our event list, events queue, then the circle event is a false alarm. So you don't need to deal with it, since as you see, this is a site event, it's not a circle event. So you should delete this event, delete this circle event, which has been actually embedded into our queue list in a wrong way. So we don't need to deal with it. We can simply remove it and make our job simpler. Any questions, guys, after the second step of this handle site event function? Okay, let's go on. So, and then what we do in the third step, we are trying to replace the leaf of T that represents alpha. If you remember in the previous slide, I have drawn something like that, and I had alpha here, right? So what I'm going to do right now is that since this one is modified, I will do some modifications on it. I will replace this leaf. Brock, do you have questions? Brock, are you there?
Yes, I'm there. I'm sorry, my hand just touched. I don't know why.
Problem. So then what we are doing, we are replacing this actually arc alpha with a subtree having 3 leaves. So instead of this one, we will have kind of 3 leaves. Why is that? Since initially, let's say we had such an arrangement, and now if we have a kind of a site here, what it will be? Yes, initially these were the sides, and again their orientation is the same kind of. So assume that this is the below is a modified beach line. And now you see initially this was alpha, and now instead of alpha we have these 3 smaller arcs. So we can represent these with the help of new 3 leaves. So the middle one will be related with our new site. This is our new site this time. Let's use the letter PI. And then for the other two leaves, we need to have kind of some tuples. These are some arc portions between PJ and PI. And the other one is between PI and PJ. So you can assume that they are kind of curved segments. And as you see now, we have two new breakpoints. If you remember the details of Voronoi algorithm, the breakpoints are highly important and they are responsible for drawing the Voronoi edges. Initially, we had a single breakpoint here, but now we have two extra. And so these new breakpoints will be stored in the internal nodes. This is an important part of the implementation. And since we have done many modifications on the status data structure, that's why we need to do some rebalancing. If you remember for T, we said that it should be a balanced search tree. If it's balanced, then we shouldn't have more than one level difference between the leaves. This is the maximum difference we can have between the leaves. And if you have problems regarding this issue, then you should perform a kind of an rebalancing operation on the data structure T so that the rest of your implementation will not have any problem. Any questions, guys? So now let's continue. This time we will have some new health edges created actually, and they should again be stored properly. They should also be taking care of the breakpoints since they are responsible for tracing out the edges of the Voronoi diagram. And the fifth one is a bit important step here. We are now dealing with handle site event, but while we are doing some computation related with the sites, you may come up with some specific cases where you realize that there is a circle event. When do we realize it? We realize it once the breakpoints actually converge. If that's the case, then we will insert a new circle event into our event queue, and obviously we need to add some pointers so that we can easily reach to some values between these data structures. So we need to add such an event and then go on with the rest of the actually main algorithm. Now we are done with the site event. Let's have a look at briefly into the circle event. How do we handle it? So if you remember in the circle events, an arc in the baseline was disappearing. So which means that if you have an let's say an arc in your data structure, baseline data structure. Again, let's draw an example here. Assume that this is arc alpha, and if it's a circle event, then that means that should be disappearing. If it's disappearing, obviously what we are going to do, we will delete it from our data structure. And again, we need to do some updates on the data structure, update on the pointers, update on do some balancing, rebalancing operations so that everything is still fine and we can continue with the remaining steps. Another thing we need to do obviously is to delete this event from the, delete any events involving our arc. Since this is not existing anymore, we shouldn't be handling any events related to alpha. And we can easily obtain them, find them by checking the pointers from the predecessors and or the successors of our leaf gamma. So then what we do, since this circle event was related with the vertices of the Voronoi diagram. So which means that if you're handling a circle event, then the result of your function should be a vertex in the Voronoi diagram. Assume that this is the Voronoi diagram, and the output of these handle circle events should be the vertices of the Voronoi diagram. And what we need to do, we need to actually store it into our output data structure, which was doubly connected at least D. So we need to store these vertices into this data structure D. And while we are handling it, since you are merging two edges and a new half edge might be erasing, so you need to store it again into the proper data structures and assign some pointers. And this is the last, actually, as far as I remember, it should be the last step. Again, as in the case of handle site events, we need to check whether we have new actually circle events. Since after you have done some modifications, you may come up with a case where you have a new circle event. If that's the case, if again some breakpoints are merging, converging to each other, then you should find this circle event and store it into the event queue. And again, the rest is the same. Do some arrangements for this pointers, do some rebalancing, and make sure that your data structures are all fine. Now let's have a look at the time complexity of this computation. The theorem says that the algorithm runs in linear arithmetic time and it uses linear storage. So why do you think the algorithm runs in linear arithmetic time? Can anyone tell me why it's not quadratic or just logarithmic? No answers, guys? I think you forgot that I will be giving some extra credits at the end of the semester who are active in these lectures. Okay, then I'm not going to discuss it. Now let's have a look at some degenerate cases. Obviously, this one is valid for only general cases, but if you come up with degenerate cases, then you cannot say that this algorithm is running in linear arithmetic time. What are these degenerate cases? If you have some sides on the same line, if they are collinear, if they are on the horizontal line, then we cannot easily handle them. And you need to have special calls, but that will make it difficult, and that will increase the time complexity. Another degenerate case is that you might have some event points which are coinciding, which means that, for instance, you may have some sites at the same location. These are, let's say, 3 sites at the same coordinate. If that's the case, then you need to remove some of these and try to solve your problem. Since we don't have a special code, special algorithm for that, so the easiest thing is to remove such duplicate points in your initial sites. Now we are done with actually Voronoi diagram of sites, and we will briefly go into some Voronoi diagrams of lines and later Voronoi diagrams of shapes. So now this time, let me show it. We were dealing with the Voronoi diagrams of line segments. This is the input. So we are not just giving a side, but instead our input is a set of line segments. And then with the help of this algorithm or with these basic steps, we will be trying to draw a Voronoi diagram for these line segments, not just for the points. So what are the differences? This time, the distance actually is measured, not obviously from a single point, but measured from the closest point on this objects. It might be a line or a complicated, let's say, polygon. It doesn't matter. We'll always look at the closest points on these objects. Again, we will be making use of some bisectors. If you have some line segments and they obviously, if you have many of these, the resulting Voronoi diagram will be getting complicated. And here you see, for instance, we have a kind of an input line segment, and this is the beach line, or we can say that a kind of arc around our input line segment. Let's focus on here. If you look at here, this is the closest point of all these points on this portion of the arc, right? So any point underneath this region are closer to the end of this line segment than to other points on this line. That's why we consider it as a single point, single Voronoi side, and draw a similar arc as we have done for the point type of Voronoi sides. But if you look at here, this is a bit different. We don't have a kind of an similar arc. Here, again, the aim is that these points are all closer to the interior regions, not to the sides, but they are closer to the interior part of this given line segment. But the upper one, this upper region, is closer to the, again, one of the end points of this line segment. So things in here are a bit complicated. We need to be careful about these and try to come up with a nice Voronoi diagram for these set of line segments. So we have some cases actually. We may have parabolic arcs if the closest point of a line on the segment is an end point. So if that's for instance, an end point, so this part is a parabolic arc, very similar to primitive Voronoi diagrams. And the closest point of the other line segment is in its interior. So this is another requirement. If you have the closest point of a line segment is an end point, and the other one is, and the closest point of the other line segment is in its interior. If you look at here, for instance, this is the closest point is an end point, and for the other line segment, the closest point is an interior point of this line segment. If that's the case, then we will have a parabolic arc. So depending on the orientation of these line segments, sometimes we may have just a single arc, or sometimes we may have straight lines, but it depends on the orientation of the given inputs. But the thing is that the disjoint line segments of all these Voronoi diagrams will be depending on the number of inputs again. So we don't have quadratic time complexity for them. They are all linear with respect to the number of inputs. The number of vertices in the Voronoi diagram, the edges, the faces, or cells, they all depend on the number of inputs again. Any questions, guys, about this Voronoi diagrams of line segments? So now let's assume that we have no lines actually crossing over each other, and assuming that all line segments are strictly disjoint, they do not have any connections, and assume that this is our set of line segments. We have n number of disjoint line segments, and here you see at the point where your imaginary line or sweeping line is at this point, and here you see this is our beach line. This time it's more complicated than the Voronoi diagram with just points. We have straight line portions, we have arcs, we have again some breakpoints as you see here. Another breakpoints, 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 and breakpoints. And another important issue is that this time the resulting Voronoi diagram will not have just lines. We will also have some kind of arcs in the Voronoi diagram. Sometimes we may have such lines, but depending again on the orientation of your set of disjoint line segments, you may have a kind of an arc in the resulting Voronoi diagram. Now I have a look at some details related with this beach line. As I mentioned, the beach line is consisting of arcs, parabolic arcs, and some straight lines. And when do we have the parabolic arcs? We can only have them when the part of this beach line is closest to a side endpoint. For instance, let's have a look at here. This is a parabolic arc, and I can say that any point on this segment is closer to the endpoint. And that's why we have a kind of an arc on the side of the beach line. But if you look at here, we have a straight line, and they all have their closest point is always the interior of the line segment, not the end point of the line segment. Yes, this is actually what it describes. Yes, if the...
Can I ask a question?
Yes, sure.
S1 line segment is parallel to that part of you just draw, right?
They should be perpendicular. This is not parallel.
Beach
not parallel.
line, parallel to the beach line of that part.
This is not parallel to, for instance, S3. Are you asking that?
No, I'm asking S1 is parallel, whether if it is parallel to the line below it, below it. Just the part below it.
Here, do you mean?
No, on the beach line.
So
yes, that part.
Line,
yes.
Right? The beach line.
Yes, that part.
So you are actually assuming that what happens if you have such a line? Do you mean a horizontal line for S1?
Not exactly. Can I draw it maybe on?
That will be quite complicated. Go with Turkish.
Hocam şey diyorum ya, Türkçe anlatması da zor aslında da. Hani o beach line'ın hemen altındaki olan part söylüyorum. Yani şu kısma paralel mi? Beach line yani S1 segmentinin altındaki beach line kısmı, yani şu line'ın oraya mı paralel demek istedim? Aynen, tam olarak orası.
No, we don't have any parallel requirements. If you look at here, for instance, it's not parallel. The thing is that any point here on this beach line all have the closest distance to the line segments, like this one. Their closest distance to any line segment is this one. Since this portion is not closer to S4, S5, or let's say S2, they are all closer to S3. And the thing is that their closest points are the interior points of S3, not the end points of S3. If you are closer to one of the end points, then that means you are on the arc. You are on the parabolic arc. But if you are closer to one of the interior regions of any line segment, let's have a look at here, for instance. This point is obviously closer to S2 and is closer to interior portions of S2. And that's why they are all on the same line. Okay. Any other questions, guys? Let's make it clear. So now have a look at another special case. This time we have point P, which is closest to two side endpoints while being equidistant from them and also from L. Then P is a breakpoint that traces line segments. So I can show it here, for instance. This one here, for instance. This is closest to two side endpoints. The first side event, the other side event, which is endpoint. This is the distance here, and its distance to the L, which is our sweeping line. They are all the same. They all have the same dimension. If that's the case, we are saying that this is the breakpoint and is tracing a line segment applying the portion of the Voronoi diagram. Let's have a look at another case. This time we have P, which is again close to site interiors. This is the main difference. This time is closer to the site interior. Let's try to find another one. But first, I want to go through the whole description. If that's the case, while it's again equidistance from them and L, then we can say that P is again a breakpoint. Again, it's tracing a line segment. So we can say that I think this one is here, for instance, or I want to find another one here, or here. Let's assume that we have some point here, that will have a similar distance and equal distance to these interiors, and it has also the same distance to the beach line. Then we can say that as tracing one of the lines of the Voronoi diagram. I think this one might be a better example. The distance to the sweeping line, distance to the interior of S2, and its distance to S1, they are all equal to each other. And we can say that this is tracing a line segment of the Voronoi diagram. So this is a nice example for the second one. Forget about the one I described here. Okay, and this one is an example for the first one. Any questions, guys, about these tracing issues? Okay, now we have another case. This time, P is closest to a site endpoint and a site interior of different sites. This time, it's not closest to the two endpoints. It's only closest to a single endpoint, and it's also closest to a different interior of sites. Again, it should be equidistance from them, and also L. If that's the case, then our break point will be tracing out a parabolic arc. This is actually the only parabolic arc which is traced out. So that should be the point actually we are discussing. So now it says that this is closest to the endpoint, one of the endpoints. And this distance is equal to the distance of this point to the sweeping line, and its distance to the interior of a neighboring, let's say, line segment. So these are all equal to each other. And as you see, if that's the case, then that breakpoint is simply tracing out a kind of an parabolic arc, and this parabolic arc will be the portion of the resulting Voronoi diagram. And obviously, as in the case of simple point size, we have circle events in the line segments, and it's very similar. Again, if you have arc is actually separating, then that means you are going to have a vertex in your Voronoi diagram, and the fundamentals are very similar to the Voronoi diagrams where we only have just points as a size. So now, as you see, the algorithm is very similar. Just the thing is that we have more cases and they should be handled properly. So we will have some extra sub-functions in the drawing of Voronoi diagrams for the line segments. But since the main algorithm, main approach is the same, we can say that as time complexity is again similar to the time complexity of original Voronoi diagrams. Here you see an example. For instance, we have how many 5 line segments. These are the inputs, the first input, the second one, third one, fourth, and fifth. And the blue ones, blue arcs and edges are describing actually the Voronoi diagram of this given set of line segments. And in this case, actually a kind of a problem. It's the motion trajectory generation problem. These are kind of assume that they are kind of robots. And this is the starting point for the robot. And then its goal is to actually reach the end point. And if that's the case, assume that these are some obstacles in the environment. And we are trying to find a way so that our actually robot will not collide with any of these obstacles. And for that purpose, we can use a kind of a Voronoi diagram. Once you obtain the Voronoi diagram of line segments, then by simply using their edges and doing a kind of a depth first search, for instance, this is the starting point. Then the first thing the robot should do is to match its center with the line, Voronoi lines or edges. Once it's done, then it can do a kind of a depth first search and try to go to the end point. This part is actually a bit thinner, so it cannot pass through it. I think the best way is to follow this one and then to left and reach to the end point. There might be different solutions. It may even go through this point and then to upwards, to left, and then to left once again and reach the end point. So it depends on these openings, whether the robot can pass through it or not. And we are trying to find the shortest path all the time. We may have some other solutions, but the amount of travel is also important. Here is actually the algorithm for this one. The input is a set of disjoint line segments, start and end points, and the radius r, which is the radius of our robot or disk. And then output will be the path which is connecting the start and the end points, so that our robot or disk will not be intersecting with any of the lines. So what we do, we first complete the Voronoi diagram and then locate our actually cells in which the Q start and Q end points are residing. And then we'll move our robot to the start point a little bit and then try to find that path by doing a kind of an depth first search. If you come up with a solution, then you can simply output this path. But if you don't have any, then you can say that we don't have such a path.